All right, good morning and Happy New Year. Um, so today we're going to have lecture number 8 in the course, and we are going to talk about classification, which is, if you remember, the second class of problems that we have in supervised learning. In the previous lectures, we've been talking about regression problems, where the response variable is numeric. And today we're going to be talking about classification problems, in which the response is categorical. So again, we're going to be walking today in this part of the course, talking about modeling and learning from models. And in particular, in this lecture, we're going to talk again about classification problems. What kind of problems can we work with? We will talk about how to evaluate a classifier, a classification model. We're going to say that there's quite many more things to look at in a classification model than in a regression model. And then we look at how to build a classifier. And first of all, we'll look at how to use regression for classification, and then two techniques, which are trees and a variant called random forests, and support vector machines. So let's talk about classification problems in general. So what are they? The thing about classification is that, again, the outcome variable, the response, the y, is nominal or categorical. So, for example, you can think about problems like the following. Imagine you work in a bank, and you need to know whether a certain person with a credit card is going to default or not default in the following month as a function of the balance in the account. So this would be the independent variable x, and this would be the response variable y. We're trying to predict whether someone is going to default or not, given how much money they have in the bank. For example, you might be interested in predicting or in estimating whether we should accept or reject a application for, I don't know, a mortgage. Maybe based on some kind of socioeconomic index of people in a neighborhood, you might be interested in predicting whether people are more likely to take the bus, the tram, or the bike. So here again, we have bus, tram, and bike. This would be the response variable, which it can be one of three categories: bus, tram, or bike. And this is the independent variable. Another kind of a problem would be, a spam detector. So given a certain email, and let's say the features are how many times each word appears in the email, then we might be interested in predicting whether the email is what we call ham or spam. So spam or just a legit email. Or you work in a newspaper, and then you might be interested in automatically classifying the news articles in different topics, such as politics, sports, economy, science, and whatnot. So the important thing here is that there is no order in the levels of the response. So it's not that politics comes before sports, before economy. The order here is completely arbitrary. There is no sense of order in the levels of the categorical variable. And this is probably the most studied problem in machine learning. If you ask anyone about machine learning, probably 99% of the times they're going to tell you about classification problems. So let's illustrate with an example. Here again, we are talking about the case in which we want to predict whether someone with a credit card is going to default in the coming month. And so here we have in orange people who did default, and in blue people who did not default. And so what we try to do is build a classifier in which we try to predict the response, yes or no, as a function of two independent variables. So let's call it x1 and x2. And so if we look at the scatter plot here, we see that there is a very clear distinction between default yes and default no as a function of the balance. So if we were to draw a line separating yeses from nos, probably would be a line going like around there. And so we see that balance seems to be a good predictor for default. However, if we look at the x2 variable at income, we see that it's not so clear, because if we look at all the points, how they are distributed along the y-axis, it doesn't seem to be any clear line separating yes from no. And that's kind of what we see here with the box plots. So if we look at the distribution of balance, this is x1, as a function of default, we see that there is a very clear difference between the two groups, between no's and yeses. However, if we look at the distribution of income, so it would be this other variable here, both distributions are kind of the same. So this is leading us to think that balance is a good predictor for default, but income is not, because there doesn't seem to be a very clear difference between the two classes. So this is more or less the intuition behind classification problems. And so in classification, again, the response takes values in a given set of classes, something that is fixed, and that's what we call the vocabulary. So what are the possible values that the response can take? You can think, for example, of a classification problem with which we try to predict some kind of yes or no, success or failure, default or non-default, things like that. Or it could be something more complex, like whether someone takes the bus, the tram, the train, the bike, etc. So this is the vocabulary. And so a classifier algorithm takes as input the features, so from 1 to p features, whatever they are, and tries to predict this y hat that belongs to the vocabulary. So tries to make a certain prediction from the vocabulary. Now, very often we're more interested in the probability of a particular instance or a particular observation belonging to each of the classes. So many times, instead of just looking at the one prediction, the one class, we are more interested in something like this. What is the probability of each of the classes given the features? So for example, what is the probability of yes given the features, or the probability of bus, tram, train given the features? So typically, this is going to involve training some kind of model, some kind of function f, just the same way we've been doing this far, and then building on top of it another function that turns the output from f into a valid class from the vocabulary. So for example, imagine that we are predicting the probability of a yes. Then we might say the prediction is going to be yes only if the output is larger than 0.5, meaning only if the predicted probability is more than 50%. Otherwise, we predict a no. So this is a simple way of solving a classification problem with a binary vocabulary, something that is either yes or no. We could just try to predict the probability, and then if it's low, we predict one class. If it's high, we predict another class. And so we have many different classification problems. One of them is what we call binary classification, which is what we have seen so far, in which the number of classes in the vocabulary is only 2. So you can think of something like yes, no. Many times we're going to find multi-class classification problems, and those are the cases in which the vocabulary contains more than 2 possible outcomes. So it's not only yes, no, it's more possible things. Imagine that we are interested, for example, in predicting the province of a city in the Netherlands, given a certain number of features about the city. So for instance, in this case, the vocabulary would contain 12 provinces, because those are the 12 we have in the Netherlands. There are other cases in which we have what we call multi-level classification, and that is the case in which a particular instance, an observation, is actually associated with more than one class. So for example, if we are trying to classify images, we have a very large vocabulary, and actually what we say is that an image contains several of houses, trees, animal, persons, car, ball, whatever. So the point is to assign multiple classes to the image, and it's just about predicting what objects do we have in an image. This is a classification problem in which we assign more than one class to one instance. There are other problems that are less common, but anyway, they're important. So we have what we call hierarchical or multi-level classification, and this is the case in which the outcomes follow a certain hierarchy. So for example, if you're talking about music and you're trying to predict what is the genre of a given track, you might think that a song, a song or a track belongs to one of metal, rock, blues, jazz, pop, whatever. That would be the vocabulary. But if you go a little bit deeper, you could also say that something that is classified as metal could also be classified a little bit deeper or a little bit more lower detail, sorry, about black metal, heavy metal, melodic metal, thrash metal, etc. Same for rock. Something could be classic rock, progressive rock, psychedelic rock, etc. So it's not only that we have this level 1 kind of classification, we can have a level 2 classification. So we could go either, high level detail or low level detail. This is called hierarchical classification. Then we also have a structured classification in which there is some kind of structure in the input, and therefore the output has to retain that kind of structure. And this is very useful, for example, in natural language processing, in which we build algorithms to try to understand natural language, plain English, for example. And so there's something called syntactic trees, for example, in which we have the input is a sequence of words. And then what we have to predict is what is the function of each of the words. So whether one word is a noun, a verb, an adjective, an adverb, etc. So there is a certain kind of structure in the input, namely the words, the sequence of words. And so the output also has to be a sequence of what we call the part of speech, what is the function of each of the words in the sentence. So as you see, classification problems can be of very different natures, more or less complicated. And today we're going to cover only binary and multi-class problems. So only the cases in which there is one possible class assigned to the observation, and it could come from a binary vocabulary or a multi-class vocabulary with more than 2 classes. So let's talk first about how we evaluate models, how we measure the model accuracy. In the case of binary classification, there are only 2 possible outcomes, either yes or no. And if we think about it, this is actually the same as a contingency table. So we could have here the true label in the data set, what it's supposed to be predicted by the model. And then here we have what the model predicted. So this is y and this is y hat. And then we have 4 possible cases. So if, for example, in reality, the true label is a yes, and the algorithm correctly predicted the yes, this is what we call a positive, then this is a positive that is true, that is correct. So the algorithm gave a positive response, and it turned out to be correct. This is what we call a true positive. The algorithm is correct in saying the class is a yes. Of course, the algorithm can also be correct in predicting no. So if in reality the true class is a no, and the algorithm correctly predicts no, that is a negative prediction, then we have a negative that is true, a negative that is correct. So these are the cases in which the model would be correct, predicting yes or no. But of course, the model could be wrong. And in reality, all models are making some kind of mistake all the time. And so we call it a false positive if the model predicted a yes, but in reality, it was supposed to be a no. This is a false positive. And likewise, we have a false negative if the model predicted a no when it was supposed to predict a yes. So this is what we call a false negative. And how we evaluate a binary classification model, it's all about looking at this table from different perspectives, whether we care more about the positives or the negatives and that kind of thing. So again, the model could be predicting in a positive or negative way, depending whether it's yes or no. And then that positive or negative prediction could be true or false, depending on the ground truth label. And so the most simple way of assessing how well a model performs is what we call classification accuracy. And the classification accuracy, what it looks at is how many true positives we have, how many true negatives. So this is how often the model is correct, divided by the total number of observations in the dataset. So in a formula, it's essentially the fraction of observations in which the true label is the same as the predicted label. And this I is what we call an indicator function. You have it here. It's going to be 1 if the condition is true or false if not. And so this is essentially looking at the fraction over the total of this condition. are the predicted classes equal to the true classes? It's just a fraction. The higher, the better. An accuracy of 1 means the model is always correct according to the data. An accuracy of 50% means the model is correct 50% of the times. By the way, depending on the field that you look at, on the literature, some people report the error rate instead of the accuracy. It's just 1 minus the accuracy. Some people prefer to report, accuracy. Some people prefer to report error rate. They are essentially the same thing. You maximize accuracy or minimize error rate. Now, the problem with accuracy is class imbalance. So if the training data set is imbalanced, meaning that there are many more instances of one class than the other. So for example, if we have data sets about email, about spam, the majority of emails is actually spam by a large fraction. Most of the emails that are sent around in the internet, they are spam. And so there are many more data points about spam than about ham. And so the majority class would be spam. Any algorithm really, unless you control for this, is going to be biased toward predicting spam because it's more likely that the algorithm is correct. And so if we just look at how often the algorithm is correct, we are not controlling for this imbalance. A useless model that always predicts the majority class is going to have a very high accuracy because most of the times it's going to be correct in just making that prediction. But of course, that prediction is totally useless. And so accuracy is not a good metric here. We have to look for different ways of accounting for the possible imbalance in the data. And again, this is not a problem only to evaluate the model, but also for training the model. We're not going to talk about it here in the lecture, but there are ways to work around this imbalance to try to prevent the model to be biased toward the majority class. There's something called over or under sampling, in which we try to resample more instances from the minority class, or something called instance weighting, in which we might say that if an instance is from the majority class, it doesn't have so much importance in the training process. Anyway, we're not going to cover them here, but just FYI, there are ways to cover for this in the training process. The problem still remains. If we have certain imbalance in the data set, then accuracy is not a good measure of model performance. So we look for something else. And that something else is usually what we call precision and recall. And what they measure is the noise and the predictions and the exhaustiveness in the predictions. And the thing is that they implicitly treat one of the classes as positive, success, relevant, or yes. So the thing that we want to detect, so to speak. And so we have precision. It's essentially measuring the fraction of the predictions that are correct, or the fraction of the positives that are correct. So that means we look at how often the model is correct when it predicts the success class, the yes or relevant or positive class. And so it's the true positives, the cases in which it's positive and correct, divided by the total amount of cases in which we predict a positive, whether it's true or it's false. So if you want to look at it from this equation perspective, here we have the cases in which the prediction is a yes, and it's the same as the true label. So that means the model is correct in making a yes prediction, divided by the total amount of times that the model predicts a yes. So it's kind of measuring the noise. If precision is very high, the model is not noisy. So we are sure that whenever the model says yes, it's not incorrect. It's more likely to be correct because the precision is high. Now, of course, a model can be very precise just by, predicting the majority class. So something that we look into is also the recall, which models or which measures the exhaustiveness of the prediction. And in this case, the idea is the same, but instead of dividing by the total number of times that the model predicts a yes, we look at the number of times that the model should have predicted a yes. So this is kind of how well it recalls all the yeses in the data set. If a recall is very high, then that means the model is very good at predicting a yes when it should. It's not missing the positives. If the recall of a model is very low, then that means the model is not good enough to detect a positive prediction or to make a positive prediction. So it's kind of missing the positives. And as you can imagine, if the precision is high, then normally the recall is low, and vice versa. So there's a trade-off normally between precision and recall. And one way to look at this trade-off is what we call the F-score, which is nothing but the harmonic mean of the two. And the reason why we use the harmonic mean is essentially that the F is going to be high only if both precision and recall are high. If one of them is low, then the F-score is going to be low. So it's a way of looking that both precision and recall are low, or one of them is, both of them are high, or if at least one of them is low. So by maximizing the F-score, we are maximizing both precision and recall. So this is another way of looking at the classification model. So how noisy it is and how exhaustive it is in predicting the positive class, whatever class that is. If we go for the multi-class classification problem, then accuracy is essentially the same thing. So it's just a fraction of times in which the prediction is correct, whatever prediction that is. And if we look for precision and recall, and the F-score, of course, then what we can do is define precision or recall for each of the classes. So how precise is the model in a class K or recall K? So another way of looking at a classification problem is the confusion matrix. So here what we have is a classifier that tries to correctly identify different clothes in pictures, I believe. And so here we have in the x-axis the predicted label, and in the y-axis we have the true label. And so essentially this is what the model should have predicted, and this is what the model is predicting. And ideally, the model should have all instances along the diagonal. So this number corresponds to how many instances in the dataset fall under this category in which the model was supposed to predict a dress and correctly predicted a dress. And so what we see here is that there is a lot of confusion, for example, here, in which the model was supposed to predict a shirt, but it incorrectly predicted a t-shirt. And as you see, this is a mistake that kind of makes sense. And of course, we have the opposite. The model predicted shirt when it should have predicted a t-shirt. That happens 73% of the times. So this is a very good way of looking at what kind of mistakes is the model making. So for instance, we see that when the model is supposed to predict sneaker, it's actually very good at not missing sneakers, because most of the times it's going to be here. Only sometimes it predicts a sandals 5 times, and 17 times predicts ankle boots. So the model is very good at predicting the sneaker. However, it kind of makes some mistakes in here. So 18% of the time, 18 times, it's predicting a sneaker when it should have predicted an ankle boot. So we see what kind of mistakes the model makes. And this is very useful to try and fine-tune the model if, for example, some of these mistakes are very important for us and we don't want to make any of those. We can look at the confusion matrix to try and refine the model. And so this is how we evaluate classification models. As you can imagine, there are many other metrics, but normally they are all looking at kind of the same thing, positives and negatives, whether they are true, they are false. Accuracy, precision, recall, and confusion matrices. That's more or less what we always look at. So let's talk about actually solving a classification problem. We know how to evaluate. We are going to be looking at some numbers now, but first of all, we need to build a model. So how can we do it? Let's first look at a very simple solution, which is using regression for classification. So as we saw earlier, if we have a binary classification problem in which the vocabulary is only yes or no, we could encode the response variable y just as a number. So something like 0 if it's a no and 1 if it's a yes. And then we can just do a regression model to try to predict yes if the prediction from the model is larger than 0.5, meaning something like the probability of a yes is higher than 50%. or really any other threshold than 0.5. We're going to talk about this in the lab. The problem with this is that the predictions are not guaranteed to be between 0 and 1, because as we know, if we just fit a regular linear regression model, the response can go between negative infinity and positive infinity. So we could have a prediction that is negative, which doesn't make any sense, or a prediction that is larger than 1, which doesn't make sense. And so we could try to do this, but there are certain problems, like here, the boundaries for the response. If we have a multi-class problem, on the other hand, then we could just encode each class with a number. Say we use a 0 for train, a 1 for bus, a 2 for bike, etc. But the problem of doing this is that this kind of implies a certain order and distance among the classes, which has absolutely no meaning. If we do this and then do a regression problem, we would be saying that there's some kind of distance of 1 unit between the train and the bus, which happens to be the same distance between the bus and the bike. That doesn't make any sense. We could do it, but again, the model would be completely meaningless. Just think about how the optimal regression line is fitted given some data set. So let's look at the problem of binary classification, this one here. We could just fit the model and see what happens. So in these plots, what we have is classification models based on regression that try to predict whether someone is going to default or not as a function of the balance. So here we have a linear model in the left panel, and we have here all the yeses, people who defaulted, and here all the nos, people who did not default. And again, it would be kind of trying to model the probability of a default. So what we see is that the regression line is actually never predicting a yes. So this is the 0.5 threshold. The model is never above 0.5. So it turns out to be completely useless. It never predicts the minority class, in this case, which is the yes. Because there are many more no's in the data set, the model is actually biased towards the no's. So it's doing a very bad job. It never predicts a yes. We could try, of course, logistic regression, which we know kind of solves the problem of having a boundary in the response. And in this case, it's perfect, because if we are trying to model a probability of a class, then that is something between 0 and 1, which perfectly fits the logistic regression framework. So if we fit a logistic model instead of a linear model, then what we have is this kind of S. And if you see kind of the threshold of 0.5 around here, let's say 2000. So if someone has a balance larger than 2000, they're likely to default. If it's less than 2000, then they're not. So you see, using a logistic regression model, we could try to solve the classification problem just by modeling the probability of default. And again, the threshold is completely arbitrary. I could choose 0.5, or I could choose something here or something there. It's just a matter of how well does the model perform. And so if we encode one class as a 0 and the other one as a 1, we just use logistic regression to predict the probability of each of the classes. And so as we know here in the link space, so notice that here we have the transformed variable. Here we have all the yeses. Here we have all the nos. We fit the model in the link space. We know that it's a line. When we transform the model again to the response space, notice that we have now a probability of default. We know it looks kind of this S. So we are predicting the probability of default given the balance. So again, we can do logistic regression to kind of solve a binary classification problem. We just work with probabilities. And there are extensions of the logistic model, as we talked about in a previous lecture, just with a little bit more detail. For multi-class problems, we use what we call multinomial logistic regression, in which essentially there is a single function per class, a single model per class. So instead of modeling in the logic, remember we model the probability of positive, the odds ratio. So a yes given, or a yes divided by a no. So this is the odds and the log. And here what we do is do the same thing for each of the classes. So what is the probability of a class K? over the probability of no class K. So this is again the odds of class K, and we just fit the model for that. So we have a model specific of that one class, and then we have a model specific of the other class, model specific of the other class, etc., etc. And so in the end, we are modeling the odds of each of the classes with a different model. And if we have ordered responses in which there's some kind of order between the classes, so let's say we're modeling an ordinal variable that is low, average, and high. There is an order between them. Low is supposed to come before average and before high. Then what we could model is the odds of the response being higher than a certain class. And it's essentially modeling the same thing. It's just an odds ratio. And the point here is that there is one intercept per class, but the rest of the model is the same across classes. And so again, we could just do logistic regression models, kind of on steroids, because here we are just modeling using multiple functions, multiple linear functions, but we can try to solve multi-class problems and ordered problems. But let's look into something more, more complicated, something that is more suited for classification. Let's talk about trees, decision trees. Let me see how I'm doing with the time. Okay. So the idea of a decision tree is that we are going to sequentially split the feature space into different regions. We want to take all the features in however dimensions we have and just split that space into different regions. And the point is that if we keep doing that, we're going to reach a point in which each of the regions, the final regions, the smallest ones, are going to predict a single class. And the rules to split the space are summarized in a decision tree. So this is the kind of model that is very useful for interpretation because it's very simple. We're going to see an example now. It's just about following a sequence of rules. The problem is that it's not very competitive for prediction. So it's very useful for interpreting. It's very easy to understand, but it doesn't work so well, or it doesn't work as well as other models. And the thing is that there's no equation. The tree itself is the model. So here's an example. This tree is built for a data set in which we have different features about patients, what kind of chest pain they have, the sex, the age, calcium level, cholesterol levels, etc. And we're trying to predict whether that specific patient has a kind of heart disease, one specific heart disease. And the model is what we see here. It's the tree. And how we interpret the tree is as follows. So we have one observation, one patient, and we look at the features. So we start over here. And what the rule says is if the chest pain is one of classes B, C, and D, so what kind of chest pain the patient has, then we go this direction. Otherwise, we go this other direction. And then we continue. So for the same patient, if he or she is younger than 57 years, then we go this direction. If it's older, we go this other direction. And then we look at the sex of the patient, whether he or she is man or woman. I don't remember now which one is 0 and which one is 1. But anyway, we go one or another direction. Let's say we go this direction. If the calcium level is lower than something, we go this direction, this other direction. In the end, we end up in one leaf node, in one of the leaves of the tree. So this is what we call the root, and this is what we call a leaf node. And so in this case, this patient, by looking at the features and the conditions in the branches, we arrive at this specific leaf node, and the prediction in there is a yes. If we arrive at, let's say, this one here, the prediction would be a no. It's just about looking at the feature values and then going through the tree, looking at the feature values compared to the decisions we have in the branches. So this is a decision tree. This is the model. And so you see the tree contains nodes that are laid out in a hierarchy. One node may have several children. and the tree is represented upside down, just because it's easier to read from top to bottom. And so the node at the top is what we call the root, is where we start making decisions. The terminal nodes are the leaves. They don't have any children, and anything other than that is what we call an internal node. And the thing is that for prediction, normally the conditions or the features that are used towards the top of the tree, those are the most useful features to separate the classes in the response. In this case, whether someone has the disease or not, because those are the ones that separate the feature space in the best way, in an optimal way, to try and predict yeses from nos here in this case. And so what we see here is that chest pain seems to be a very important feature, and then age and calcium level. So this is a tree, a decision tree. You see, it's a very simple model. The thing is that all instances, one way or another, they're going to fall into one leaf node. And that leaf node is going to be assigned the same class again. So any instance that fall under that leaf, is going to have a prediction equal to the class most commonly observed in the training data. So if in one particular node, let's say this one, we have yes, yes, no, only 3 observations in there, then the prediction for all these 3 observations is going to be a yes, because that's the majority class. And then whenever we have a new instance, something coming from a validation set or a test set or just a brand new patient, if the patient falls under here, we are going to predict yes. Of course, we can make probabilistic predictions. So we could say here something like the probability of yes is 2/3 and the probability of no is 1/3, because that is what we observed in the training set. But normally we just look at, the one class. What is the majority class in that leaf? And whenever we want to make a prediction, we just go through the tree, end up in a leaf node, and look at the majority class. That's it. So you see, it's a very simple way of making predictions. There's no equation, it's just following rules. And what we saw is that a tree is essentially splitting the feature space into regions. Each of those branches splits the feature space in 2 different regions. And so ideally, wherever we decide to split the feature space, it should maximize some measure of model accuracy. You could think of precision, recall accuracy, that kind of thing. We're going to say that we actually use something else. One way or another, we are expected to be making a good decision, meaning that we are maximizing the model accuracy. So this implies a partition in an arbitrary number of irregular shapes. We could be splitting, imagine that we are using 2 features. That could entail a split that looks something like that, for example, something that is very weird. And coming up with those boundaries, with those decisions, is actually very expensive and computationally inefficient to do. So what we do is follow a top-down greedy approach, splitting always in 2 in a linear way. So we do it top-down, meaning we always start from the root of the tree, going all the way down to the leaves, and we do it in a greedy manner, meaning that at any given point in the tree, we always make the best decision at that point, without looking forward and without looking back. So it's not that we start making decisions and then say, turns out that this is not a very good split, so we go back and look for some other split. We don't do that. We do it in a greedy manner, meaning at any point, we just make the best decision possible and don't look back. So it's all about splitting the feature space in regions so that we end up with boxes. Recursively, by splitting the feature space, we end up with different boxes, different regions. And so the point is, for any given split, we select one predictor, let's call it predictor number J, and select the cut point T, such that we make the following rule. If the value for the feature is less than T, we go to one region. If the value for the feature is larger than T, we go to the other region. So we are splitting at x sub j equal T. And then we repeat the process in each of the 2 regions separately. So we do it recursively all the way down to the leaves. And so you might be wondering already, when do we stop? We're going to talk about it later. So let's say, imagine that we have again two features, x1 and x2. It's impossible to have a decision tree make boundaries like this, because this would not be possible to achieve in a greedy manner. What we could do is something like this. And let me show you what happens. So the first decision was about feature x1. We chose this threshold t. And so the point is, we are first defining this boundary. Whenever x1 is less than t1, we go this direction. Otherwise, we go this direction. And then we go into these two regions and repeat the process separately. So we first go to this part and look at conditions. Turns out that the best condition, the best split, is about variable x2. And we come up with this other threshold, t2, over here. So if x2 is less than t2, we go to this region, region 1. If x2 is larger than t2, then we come to this region R2. And let's say that because of some condition, we stop there. We're going to talk about it later. Then we continue with the other region we had here. The third threshold is going to be again about variable x1. It's this one here. And that divides the space into this region and this region. And then we repeat in both of them. Let's say that in R3, we don't do anything else. We don't go farther in the tree, but in this other region, we do. And we actually choose a threshold T4 for variable x2 that determines this region here. So we have regions 1, 2, 3, 4, and 5. Each of those corresponds to a leaf node, and each of those is going to make a different prediction, a different class. The structure of the tree would be something like this. So at the root, we have the first condition, which was about threshold T1, and then we go left or right, meaning we go to this part of the space or this part of the space. And then we make a decision based on threshold 2 for x2, which determines region 1 or region 2, and all the way for the other part of the tree until we reach regions 3, 4, and 5. So this is how the algorithm works. It's going to split the feature space. Again, this is only 2 dimensions, but think about a multidimensional space. The tree is just going to work the same way, splitting in subsequent steps in 2 parts, left and right, based on some condition. And so the decisions to split are made on the basis of some kind of measurement of the model accuracy or the model error. So let's define P sub mk to be the fraction of instances in one region, region M, that belong to class K. So what is the fraction of instances in region M that belong to class K? A natural measure of the accuracy of the region is going to be the fraction of the instances in the training set that are correctly classified. So we know that the prediction of the region is going to be the class with the higher P. And so the accuracy is what is the maximum P? What is the class, or actually what is the accuracy of the prediction? How many instances we have of the majority class? This is a natural way of deciding whether a region is good or not. So are the predictions going to be good or not given the training set? Turns out not to be a very good measure, and in reality we typically use one of these other 2, the Gini index or the cross entropy. The Gini index is defined in this way. It's kind of a, if you're familiar with statistics, this is kind of a variance of a Bernoulli variable. So it's looking at all the classes in the vocabulary and computing this number. And so this is going to be minimized as each of the P's get closer to 0 or 1, meaning all the instances belong to the same class. So imagine that we have a perfect node in which the prediction is going to be always perfect. All the instances belong to the same class. Then this P is going to be 1 for one of the classes. So the contribution to the summation is going to be 0. The whole thing is going to be 0. So the Gini index of 0 means perfect. So yeah, this is essentially what we have here. Any other case, this Gini index is a measure of some kind of node purity. So how pure is the node in the sense of, that all the instances in the leaf belong to the same class. In that case, the node would be pure. If we have, kind of a uniform distribution of instances in the leaf, like same amount of yeses as no's, then the purity of the node would be low, because any given prediction in there is going to be kind of random. So we want to have leaf nodes that have a high purity, meaning most of the instances belong to the majority class. So that's one criterion, the Gini index. Another criterion is the cross entropy, which is just looking at something very similar, at the entropy of the nodes. High entropy is a bad idea, low entropy is a good idea. So these are measures of the model error. They are actually minimized. We want to have a Gini index that is close to 0 and low entropy. And those are the two most common criteria that we follow in order to build trees. So at any given point, if we are thinking about making a split at one specific point of the feature space, we look at the Gini index and the cross entropy of the two resulting regions. If it's good, we continue. If it's not, we look for something else. And so the point again is that if we continue splitting indefinitely, we may end up overfitting the model. Because think about it, if we continue splitting the feature space into different regions, at some point we're going to end up with the case in which every training example is going to have its own leaf. So we're going to have a very large, a very deep tree in which every leaf corresponds to only one instance in the training set. That tree would be overfitted. That's a perfect example of overfitting. So we have to consider options for reducing the size of the tree to prevent overfitting. Essentially, that means, a fewer number of nodes, or small number of nodes, or a tree that is not that deep, things like that. We can continue, or we can choose different options for doing this. And the point is that we are going to gain a little bias. So the model is not going to perform so good, but we are going to reduce variance. So the model is not going to be so dependent on the specific training data that we have. So the thing is, we use smaller trees or prune an existing tree. That's the idea. We just restrict the process of training the model, or we just get a full model and then prune it at some point. And the thing is about, again, avoiding a split if it results in regions with very few instances. If we end up with leaves with only 1, 2, 3 instances. So these kind of thresholds are what we call hyperparameters. So if we set a limit on the depth of the tree, or we set a limit on the number of leaves, or we set a limit on the minimum number of instances that must fall within a leaf, all those parameters are what we call hyperparameters. And they are hyperparameters because they are not really parameters of the model. They are rather parameters of how we train the model. That's why we call it hyperparameters. So those are parameters that we have to tune when training the model. And a very typical question to ask is, how do we choose those parameters? The answer is usually cross-validation. We're going to see an example. So the important concept here is that we have these hyperparameters that allow us to control how the model is built. So let's say here we have a full tree about the same data set, trying to predict if someone has the heart disease or not. You see that it's a rather big tree, and specifically we see some weird things in there. So for example, here in this case, it turns out that whether cholesterol is low or high, in both cases we predict a no. Now, the reason why this is happening is that the purity in one node is different from the purity in another node. If we just look at the class prediction, we are going to predict the same thing, no, regardless of whether we are in one leaf or the other. But maybe we are more likely to be correct here than in here if there's many more instances of the no in there than there are in there. So if this is, let's say, node 1 and node 2, the purity of node 1 is going to be maybe higher than the purity in node 2. So if we make the prediction because of node 1, maybe we are more likely to be correct. But if we're not interested in that, maybe we can just prune the tree and say, hey, anything that falls under this branch is going to be predicted a no, and that's it. Same thing here. Anything that is predicted there is going to be yes. So we could try and prune the tree there and there, different places. Or if in here we only have one instance, there's no point in making all these branches to just this one instance. Whatever we end up here, we predict a no. So this is how we can prune a tree. And of course, we are going to do this automatically. It's about looking at what the leaves are and how they behave and make decisions about pruning the different branches of the tree if it makes sense. So we could try and do cross-validation. Say that one hyperparameter is the tree size. This is the hyperparameter, the tree size. We're going to train the model, restricting the maximum size of the tree. And normally this corresponds to the number of leaves. So how many leaves are we going to permit the tree to have? And then it's about doing cross-validation. So you know the drill. You split the data into different folds, and you build the model in some of the data. Then you validate the model by evaluating the performance on a validation set that was not used during training. We do this multiple times, etc. And we could make a plot like this. So for the different values of the tree size, we could plot what is the error or the accuracy or any other measure of model accuracy that we want to use. And as we know, if we only look at the performance of the model in the training data, which is the black line here, we know that it's going to decrease as we make the model more complex. If we think back about the lecture on models, we know that if we make models that are more and more and more complex, we are going to minimize the error in the training set because we are overfitting. So that's why the black line continues to go down as we make the model more complex. That makes sense. The important point is, how is the model expected to perform on unseen data, on a test set? So we could do cross-validation. And it turns out, this is the orange line, if we do cross-validation trying different hyperparameters, different sizes of the trees, we see that it's coming down. It's improving as we make the trees larger, but at some point it's going to start overfitting, and so the validation error is going to start increasing again. So if we were to make a decision of what is a good size of the tree based on cross-validation, we would be looking at the orange line. We know that the black line, the training error, is going to decrease. We have to look at the orange line. At what point is it low enough in this case, because this is an error, is it low enough that it doesn't make sense to go farther than that because the model starts overfitting? And so it would be somewhere like around here. If we plot the orange, it's something like that. So around there is where we make the decision. The hyperparameter that controls the number of leaves, it's around 6. And so what we do is we build a model restricting the training process with the hyperparameter number of leaves equal 6. And it turns out that it gives us this tree in which we have 1, 2, 3, 4, 5, 6 nodes. Now, normally the performance of this model is going to be lower than this one, but the point is it's not going to be that much lower. That is the point. And however, the model is much simpler. It's only a few decisions to make. So this is in general how we tune the hyperparameters. We just do cross-validation, looking at a range of values here for the hyperparameter, and then look at some measurement of model error, accuracy, whatever we are interested in. And it's just about making the decision. What is the sweet spot that looks like a good value for the hyperparameter? And we could do this for the number of leaves, as in here. We could do this for the depth of the tree. We could do this for the minimum number of leaves, the minimum number of instances that fall under a leaf, etc., etc. So we could choose essentially any hyperparameter that we want. And so trees are very easy to interpret. It's just about following rules. We go through the tree and just make decisions. It's going to be easy to display graphically and explain because the model is the picture. And it's very easy to handle quantitative predictors, categorical predictors. We don't need any dummy variables in the model. If we have any categorical predictor, like in here, it's just going to say, are you, value A, B, C, D, things like that. Then you go this direction. Otherwise, you go this other direction. We don't need to use any dummy variables. And if you think about it, it kind of inherently handles interaction terms through the tree structure, because here we have one specific value for the feature, for x1, let's say. If we count this direction, and this is feature x2, if we go this direction, is the specific combination of features x1 and x2 in this side. In this other direction, we have specific combination. If here we have x2, again, these are the 4 possible cases of the interaction term between x1 and x2. So interaction terms are implicit in a decision tree, something that we had to explicitly specify in a regression model. We don't have to do in a decision tree. The problem again is that they're not very competitive in terms of prediction. If we look at other techniques, we're going to look in the second half of the lecture, trees don't work that well. They're very easy to explain, to predict, to interpret, but they're not very good at predicting. So I think we're gonna break here. Just FYI, we can also use trees for regression. The idea is the same. It's just splitting the feature space into different regions, and then for each of the regions, we just make a different prediction that just happens to be a number. So just like in a classification problem, we predict the majority class. In a regression problem, we predict the average of the responses in the region. Anyway, we're not going to talk about it, just FYI, and we could use classification trees for regression. So let's break here. Then after that, we're going to continue with random forests. And I'm going to start reading questions and try to answer them when we come back. So it's 15 to 12. So let's come at 12 sharp, and then we continue. If you have any question, post it in the Q&A, and I'm going to start answering when we come back. See you in 15 minutes. Okay, so we're back. We had a couple questions, and I see that one of them was posted quite early. Sorry that I missed it. One of them was, is recall the same as sensitivity? The answer is yes. And I wanted to show you this Wikipedia page about the evaluation of binary classifiers to show you that there are many different perspectives on this confusion matrix on the table that we saw earlier. And in different fields, people call the same thing differently. And in different cases, you are more interested in one thing or the other. And just so that you see, there's plenty of names for the same thing. So as you see here, sensitivity is the same thing as recall. Normally, again, we look at recall, precision, miss rate, and false discovery rate. Those are the most typical ones. And again, it depends on your case. So for example, imagine that we are developing a new test for the COVID-19. Then you want to make sure that if someone has the virus, you don't miss it. So you don't have any false negative. If you predict no, you have to be very, 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 very sure that the person indeed doesn't have the virus. But you don't want to miss someone who does have the virus, and then you predict a no, because that person could die. If you predict a yes when someone does not have the virus, then the impact is going to be lower. So in this case, we want to have a test with a very high recall. If someone does have the virus, we want to make sure that we predict it, even if that makes some negative results, some not negative, sorry, some false positive results, because we can always repeat the test. So again, depending on your case, you want to make sure that whatever criterion you want to follow is maximized, and that could be many different things. If you work in the case of detecting spam, then you want to make sure that you never misclassify as spam an email that is not spam, because probably the person is not going to see it. If you mistakenly, let some spam email go through your inbox, it's not so bad, because we can always just say, hey, this is spam, I don't care. But we don't want to go through the thousands of spam emails just to see if the classifier made a mistake. So depending on your case, you want to look at different things. And the other question we had is this thing about building the tree, coming up with the splits, with where to prune and everything. Do we have to do that manually? The answer is no. Of course, we have software to do that. In the lab, you're going to see how to do this in Python. You can always fine-tune the tree manually if you want. So for example, in a case like this, you might be interested in pruning in a specific place, like, I don't know, in here. I'm going to say that I forgot about this one and prune there. You can always do that manually. But normally what you do is you set the hyperparameter for, in this case, I don't know, the number of leaf nodes, and then you let the algorithm come up with the best structure conditioned on that requirement. And that's fine. So normally it's all automatic, but of course you can do things manually. Okay, so those are decision trees. Again, if you have questions, feel free to answer in the Q&A. I'm going to try and keep an eye on them more closely. So we have random forests. This is the next step for decision trees, which is essentially just training a huge model with many different trees. That's why we call it a forest, and we're going to see why this is a very nice idea, a very simple idea that works actually very good. So bagging is the first technique that we're going to see BO4 for random forests. So the thing about trees is that they can grow very deep. You can build a huge tree that is in the direction of overfitting, and that tree is going to have low bias, so it's not going to make a lot of mistakes, but it's going to have a very high variance. So it's going to have a very different structure depending on what training set you use to build the model. And this is not good. So we saw we could always prune the tree, and that's going to reduce the variance at the cost of increasing the bias. Is there any way of reducing the bias while maintaining, reducing the variance while maintaining the same bias? And the answer is yes, it's bagging. Bagging is a general purpose technique. It's not only applied to trees, you can apply them to or some other classification. But it came out because of trees. So the thing is that they're going to reduce variance, maintaining the bias more or less. And by the way, this is also called bootstrap aggregation. The idea is very simple. So we're going to create multiple trees, multiple models, trained with different training sets. And then in the end, whenever we want to make a prediction, we run the new observation through all the trees, and then kind of average the prediction of all those trees to make the final prediction. So it's like building many different models of the same kind using different training data, and then having a kind of average prediction. That's the idea. And the thing is that each of those individual models is going to have a low bias, but a high variance. However, because we average over multiple models, we're going to reduce the variance. That is the idea. And so the problem is, very nice, but where do we get these multiple training sets from? Normally you only have one, and you build the one model with that one training set. So how do you come up with multiple training sets? Then we do something very similar to what we saw with cross-validation. We basically bootstrap them. And that means we sample with replacement from the full training set. So for the final prediction, we take the class that is most often predicted across the trees. That would be the majority vote. So let me draw the picture for you. Let's say this is the full training set. Then what we do is we create a new training set. Let's say this is T. We call this one T1. And we make it by sampling with replacement from here. And there we build the first model. Then we build another bootstrap training set, again by resampling from here, and we build a second model. And we do this multiple times, up to m, I don't know, some n. If we want to make a prediction, then for some new data, we make the prediction for model 1, the prediction for model 2, all the way to model n. We have those predictions. And then we take all this and aggregate in some way. In the case of classification, we just take the majority vote. So which is the class that is most often predicted in all these entries. And that would be the final prediction. So this is how bagging works. It's just creating all these different training sets by resampling from the training set we have here. If we want to make probabilistic predictions, it's just, looking at the individual predictions of the trees and just predicting the empirical distribution that we got there. That's fine. So this is the idea. By averaging the prediction over multiple low bias models, we are going to have low bias but reduce the variance. So the model is not going to be so sensitive to the initial training set we have. The problem with bagging is that all those trees are going to be correlated in one way or another. Because if you think about it, they are based on very similar data. After all, we're just resampling the same training set over and over and over again. The data is going to be very similar, and we have the same features. So all those n different trees are going to be very similar one way or another. So one way to reduce variance even more is to decorrelate the trees somehow, to make them more different. How can we make them more different? Well, one alternative would be using different data, but we don't have different data. We normally have only the one training set. We can't go this direction. We can go this other direction. We can just use different features. So the point about random forests is that for each of those individual trees, whenever we have to make a new split, then we're going to use a random selection of m predictors, normally m less than p. So instead of looking at all the features that we have available to decide where to make a new branch, we're going to randomly select a set of only m features, and we only make the branch looking at those m features. We do this for every split of every tree. And so by doing this, the trees are going to be more different to one another. The bias is going to be higher because, after all, we are restricting the capability of the model to make good splits. We are restricting the feature space in each split, and so the individual tree is not going to be so good. But when we average over multiple trees, we're going to kind of get rid of that problem. So we have to make a decision about M. This is, again, yet another hyperparameter. Normally, we use something like more or less the square root of the number of parameters that we have. But this is, of course, something that you can hyper tune. You can tune through cross-validation or any other criterion. And so the idea, again, about the random forests is that we make the trees more different to each other by restricting what features we look at when we make a decision. I have a question. How do you resample from the sample set? The thing about sampling is, imagine we have, let's say this is a bag of balls. So we have a ball that is blue, blue, red, red, green, 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 yellow. Let's say this is our training set. If you sample from here, then you could take one ball, take it out of the bag, right? That would be a blue. Let's say you sample another ball, it would be this one, you take it out of the bag. If whenever you take the ball and sample it, you put it back into the bag, you could resample the same instance, right? This is what we call resampling. So you take with replacement, that's what we call with replacement. So you take the same training set and create a new sample of the same size by sampling the instances with replacement, meaning whenever we sample one instance, we put it back into the bag so it could come up in the training set again. So here we could have multiple cases of blues, red, yellow, and no green, for example. This is how we do it. And so this is a random forest. It's just a way to take a bagging and do it a little bit better by making the trees more different to each other. And then if you do something like cross-validation, or if you want to see how well the trees perform as a function of the number of trees that you train, so again, this is a hyperparameter, you could decide to train, I don't know, 5 trees or 100 trees or 5,000 trees. It's up to you. This is yet another hyperparameter, something that you have to tune. And so the thing here is that, you know, in this case, we're looking at classification error, so lower is better. If we build a single decision tree, we are there. We have an error of about 0.3. Let's say this is a tree that has already been pruned, etc., etc. If you start building more trees in a bagging fashion or a random forest fashion, then you see that performance is going to increase very rapidly. So the error is going to decrease very rapidly. And at some point, it kind of converges and stays the same, right? So by looking at a picture like this, we would say that a random forest classifier with about, let me say, I don't know, 30 or so, about 30 trees seems to be the best option. So the important thing here is if we start bagging or doing a random forest, performance is going to be better, but at some point it's going to converge to some minimum, and that's it. You have to select this sweet spot. Again, this is just another hyperparameter. So this is random forest. It's again a very nice, a very simple idea that actually yields a very good performance. It just requires more computational cost, or it has higher computational cost. So this is how we can build a classifier with trees, either a single decision tree or random forests. And then the final technique we're going to see to build classifiers is what we call a support vector machine, or SVM. And they are also a very clever idea, I have to say. So the idea of the SVM is that we find a hyperplane that separates the classes in the feature space. It's essentially just, Imagine that the feature space is only two features, x1 and x2. It's about finding the line that separates the classes between these guys and these guys. That's the idea. If we go to multiple dimensions, then it's something more complicated. It's not just a line, it's maybe a plane or something more complex. The thing about it is that it does not provide a probability of a class, just a class. So it only says whether you are below the line here or above the line, nothing less. There are some extensions that allow for this, but they typically involve training logistic regression models on top of the SVM. We're not going to talk about them. So we're just going to make this class prediction. And the thing is, if it's not possible to separate the classes just with this one line, we're going to try two things. First of them is relax the definition of separation. So we're going to make it kind of soft. We're not going to look for the line that separates perfectly, but one that separates optimally in some sense. We're going to talk about it later. And the other one is that if a line is not enough, then we're going to start transforming the feature space so that we can fit something that is not a line. So we're going to talk about it later too. Again, they're a very powerful idea. They come entirely from computer science. They have very little use of probability models. And they can also be used for regression, by the way, just like the trees. But again, we're not going to talk about them here. So it's about finding this hyperplane that separates the classes between yes and no, above, below. That's the idea. So let's see. Here we have two features, and we have a binary classification problem. So the instances belong to the white group or the black group. And here we have three different hyperplanes. In this case, they're just a line. So if we look at the hyperplane number one, the green one, we see that it's not very good at separating the classes because it would separate things that are to the left, things that are to the right. And then we see that it would make a lot of mistakes because all these points would be misclassified as white. So that's not a very good hyperplane. It's not doing a good job. If we look at the second hyperplane, the blue one, we see that it's actually very good because it separates perfectly the classes. Everything to the left is black, everything to the right is white. This is good. It's predicting perfectly all the instances. However, if you look at the hyperplane number 3, it looks like it's probably a better decision. If you look at it intuitively, it's because the distance between the hyperplane and the points, it's maximal. So all these observations are very close to the boundary. All these observations are very close to the boundary here. So probably if I have a point in there, it should be a black point, not a white point. This is the idea. And vice versa, if we have an observation in this point of the feature space, it's probably a white observation, not a black observation. So this is why hyperplane number 3, it's probably a better option because it's maximizing the distance between the hyperplane and the observations. And that's essentially the idea of the SVM. So a hyperplane, this is what we have been talking about. It's just a fancy word for, if you have a feature space with 2 dimensions, 2 features, then we're talking about a line. If we have a feature space with 3 dimensions, then we're talking about a plane. If we have only one feature, then we're talking about a point. So it would be only one feature, x1, and the hyperplane would be this point. You are to the left or to the right. That's essentially what we're talking about. It's always this linear model in which we have one fewer dimension than the number of features. So you see, it's all again back to the linear model. It's fitting a linear model, defining this hyperplane that separates the classes. So the idea of the separating hyperplane is very simple. It's just fitting that one linear model, that function f, that separates classes between, in this case, blue and pink. If all the points are correctly classified, then this hyperplane defines what we call a separating hyperplane. It's a hyperplane that separates the classes. So you see all these lines in here, they are all separating hyperplanes. They correctly separate all the instances between blue and pink. And of course, the thing is about choosing one of them, the one that is optimal in some sense. So how do we choose it? Then we talk about the maximal margin classifier. So the point is, there are many hyperplanes to choose from. We have to select one. How do we do it? Then we choose the one that maximizes the margin M. And the margin is nothing but, well, actually it's a margin. If this is the hyperplane, the margin is what we have here. So it's a certain distance M that is maximal, such that any observation is farther than M units from the hyperplane. So if we draw this margin, we know that every observation is on this side of the margin, and any observation here is on this side of the margin. If we have a hyperplane with a very high margin, that means all the observations are far from the hyperplane. That's good. That's what we want to maximize. If we have observations very close to the margin, let's say over here, then maybe we are misclassifying this point. So we want to choose the one hyperplane that maximizes the margin. So that is that all instances are beyond that point, are farther away from the margin. That's what we want to maximize. And it's about choosing that one, the one that maximizes the margin. That's the hyperplane that we choose. The problem is that linear functions are sometimes not capable of perfectly separating the data. So if we look at this example here, it's impossible to find a line to separate all those points. It doesn't exist. It doesn't matter how long you take trying to find it. It's not going to be possible because there's no line separating all these observations. And so the maximum margin classifiers are not enough here. And they're also not robust to noisy data and outliers. So here we have the same training data that we saw earlier with this one addition. This was the hyperplane that we defined without the outlier. If we add this tiny outlier, look at how much the hyperplane is going to change. Because again, we are requiring that all observations are on the right side of the hyperplane. If we have one outlier or something that it's, we have data that is not very robust, it's noisy data, then the model is going to have a very high variance. It's not going to be a good thing to require all observations to be on the right side of the margin. So it should be okay to make some kind of mistake if the hyperplane that we choose is better. So that's what we do. Instead of requiring this hard separating hyperplane, then we go for soft margins. And the idea is that we are going to give some kind of slack to the margin. We can define some kind of budget C. This is again another hyperparameter, such that every observation is going to be allowed to deviate from the margin a little bit, or to be in the wrong side of the margin a little bit. So let me show you this example here. We have again two features. Blue and pink are the classes. We have here the hyperplane and the margins. So we see that this hyperplane is perfectly separating the classes. Everything on top is blue, everything on the bottom is pink. So every observation is in the correct side of the margin, of the hyperplane. However, this observation number 8 is on the wrong side of the margin because it should be over there. It should be farther away than the margin. However, it's inside the margin. This is wrong. Same with this one. It's on the correct side of the hyperplane, wrong side of the margin. And they are wrong by a certain amount. In particular, this observation 8 is wrong by this amount. This observation 1 is wrong by this amount. So it's about allowing for these deviations from the margin as a function of how far they are. And so instead of requiring every blue observation to be there and every pink observation to be here, we are going to allow for all this. We're going to give some slack to the observations. And it could be even something like in this picture here. So it's not only that we have observation 8 on the wrong side of the margin. We have, for example, observation 11, which is not only wrong side of the margin, but also wrong side of the hyperplane. Here we have a wrong classification. So this 11 is going to be classified as blue because it's on this side of the hyperplane. The slack that we're giving to that point is this much, because it should be beyond there. Now, in this problem, or in this case, let me delete. In this case, all points are correctly classified. In this case, point 11 and point 12 are misclassified, but maybe the hyperplane is better. That's the idea. So we are going to give some slack to the margins. That's the idea. This budget that we give to the classifier is just another hyperplane that we have to tune. And if you think about it, only the points that are within the margins are the ones that are determining where the hyperplane is going to be, because the other ones, all we know is that they are farther away from the margin. We don't care how far, we just care that they are farther away than the margin. So we could hypertune the cost, this budget, to control how the model is built. And the thing is that if you increase the budget, then you're going to lower the variance. You're going to make more mistakes, therefore you're going to have higher bias, but you're going to lower the variance because you're going to allow the margin to be soft. If you decrease the budget, then you are requiring the model to go for strict margins, or sorry, strict hyperplanes, even at the cost of making mistakes, or of not making mistakes. It's not going to make mistakes, but it's going to have a very outlier hyperplane. So if you change the training set, it's going to vary a lot. So you're going to have a low bias. You're going to have more correct predictions, but it's going to depend a lot on the training set. You're going to go for overfitting. So again, it's something that you have to hypertune. How do we hypertune? Again, cross-validation. So here you have an example. In this case, we have a very large margin. We can see it in the picture. And essentially, all the observations are on the wrong side of the margin. All the observations are within the margins here. If we start decreasing the margin, then we see some of them are outside the margins. That's good. If we decrease even further, in this case, more observations are outside the margin. And you see that we start making mistakes. Like in here, we have only a few mistakes in there. Now we are reducing the number of mistakes. And all the way to this case with even lower margins. So that's one point, to make the margins soft. The other one is, hey, sometimes it's just impossible to find a linear boundary. It just doesn't exist. If you think about this example here, there's not one single line that fully separates in blues and pinks. It just doesn't exist. If you fit the support vector machine to this model, you're going to have this one, which is completely useless. So what we have to do is try and transform the variables. And there's the idea, to transform the feature space in many different ways. So you could think about, for example, having feature 1 squared, feature 1 to the power of 3, feature 1 times feature 2, feature 1 times the square of feature 2, many different transformations, polynomials, logarithmics, exponentials, Gaussians. There are many different ways of transforming the variables. And the idea in general is to go from the P features that we have to Q, something that is much larger. So in the end, we're going to start with the same features. We transform them in many different ways such that the feature set is actually much larger. And then the SVM is fitted in that transformed feature space where we have many more dimensions. And the thing is that in those many more dimensions, we still fit a linear model. But when we come back to the original P features, that model is not linear anymore. That is the point. So we go to a higher dimensional space, we fit a linear model in there, and then when we come back, we have non-linear hyperplanes. So that's the idea. In this case, we have two features, x1 and x2, and by doing some transformation, which is polynomial in this case, I believe, we are able to come up with a hyperplane that is defined by this curve and this curve. So you see, it has more dimensions than just two. In higher dimensional space, it's in one line or one hyperplane, but when we come back to this only two dimensions, it's this way. So anything over there is blue, anything over here is pink, pink, blue. And of course, we have the margins around the hyperplane. So this is the idea. We are able to do this. And of course, it's going to be nearly impossible to interpret because we are fitting the model actually in a much higher dimensional space. There's no way that we can make sense of that. But hey, if it works well for prediction, that's good. And so how we transform is controlled by what we call kernels. We're not going to talk about them anymore. It's just know that there are many different functions to transform. That's what we call kernels. And of course, they can be controlled with different parameters. So yet again, here we have more hyperparameters. You could choose a different kernel and a different configuration for the kernel. So for example, in this case, we have a polynomial kernel with degree 3. So we are making cubic transformations on the variables. Here we have a radial kernel, which is using a Gaussian distribution underneath, and this is a very non-parametric model. The thing about it is that you can do things like this. So if you use a radial kernel, the hyperplane is going to be this one here. Again, we have a margin and a margin. So you see, in this case, we have everything inside, inside the circle is going to be pink. Everything outside is going to be blue. And you see that it has a very wide margins. Everything in here belongs to the margin and in here. But it's very good at classifying blues and pinks. So it's all about finding the right transformation. And hey, we have been talking about SVMs only for binary classification. How do we do it with multi-class classification? So it's not only blue and pink, it's not only above or below, left or right. We have multiple classes. Then we have two strategies. The first strategy is called one versus all. And the thing is that we feed as many classifiers as classes in the vocabulary. So what we are predicting is one class versus the others. That would be one classifier. Then we have a second classifier predicting class 2 or one of the others. Then classifier number 3 predicting class 3 or one of the others. And then the idea is that we choose the class for which the observation is, at the highest distance from the hyperplane. That would be the one. The other strategy is one versus one. So essentially, we build a classifier for every pair of classes. So one classifier for class 1 versus class 2, then another classifier for class 1 versus class 3, then class 1, class 4, etc., etc. And it's about, in the end, choosing the class that wins in most cases. That would be another way of doing that. And again, just like with the trees, all this is done transparently for you by the software. You don't have to train all these models yourself. You just say, this is my matrix of features, this is my response, fit the model, and then underline, there's going to be many different hyperplanes, but you don't need to care about it. So this is the SVM. There are many other classification algorithms, from something simple as beta regression for binary cases to k-nearest neighbors that we talked about in the first lectures. We have, of course, neural networks, deep learning. There are many different techniques. We covered the basics today, but if you're interested in more about classification, feel free to read. You have some pointers in the end of the slides. And then finally, I want to briefly talk about model selection. It's going to be just a couple of minutes. So what happens with model selection? Hey, if you're building models and you only care about prediction, then what we typically do is use all the features that we have. And we do not care about how complex the model is. So we try as many different possibilities as we have with the hyperparameters. We try the most complex algorithm, the most complex hyperparameters, and just give it all the features that we have, and that's it. It's just model selection reduces to tuning the hyperparameters. So you give it all the data, and you don't look at distributions of errors, and interactions between variables, etc., etc. You don't do feature selection like we do in regression. So what you just do is give it all the features and just make a good selection of hyperparameters through cross-validation, and that's it. So you have to choose the family of models, you have to choose the hyperparameters, and you just have to train the model, and that's it. In the end, you measure the model performance with out-of-sample metrics. So something like cross-validation or the test set, if you have it, then you compute accuracy, F-score, precision, confusion matrices, whatever. And then you choose whatever criteria, and you tune the hyperparameters to maximize that criteria. And you have to make sensible decisions here, sensible choices. So you have to choose the metric that makes the most sense for your problem. So think about, are the classes balanced or not? Do you have a single class problem or a multi-class problem? Do you care about the noise of the predictions? Do you care about exhaustiveness? Do you care about both? Are all cases equally important? And are all mistakes equally bad? So again, if we are working on a test for COVID-19, you want to make sure that you never miss a positive case. So you have to look for that specifically. And whatever criterion you choose, again, you choose the model that maximizes that criterion, and that's it. It's usually a good idea to look at several metrics, not just the one, but have certain priorities. So for example, you might want to maximize the accuracy, but minimize the confusion between tram and bus, because we never want to make that confusion or that mistake for whatever reason. So normally it's going to be some kind of hierarchy of metrics, and you start maximizing one and then the other and then the other, etc., etc. If all you care is prediction, if, however, you are interested in understanding the relationship between the features and the response, then you have to make certain decisions. So for example, if you use decision trees, they are going to be very simple to understand. You're going to see very clearly which are the features that affect the response or that are more associated to the response. If you use an SVM, there's no way that you're going to see that. If you use random forests, it can be difficult to understand and to make sense of that, but there are certain statistics of feature importance based on how they behave across all the trees. You could do just regression models because we see that they're easy to interpret. You could start playing with interaction terms. You can do many different things as we saw in the regression lectures. Maybe that's what you have to do in order to understand the relationship between features and response. And in the end, fitting a good model here is again an iterative process. It's about fitting one model, looking at the scores, looking at the residuals, incorporate new terms, remove terms, look at significance, etc. What predictors do you start with? Just like in a regression problem, use domain knowledge, pre-specified hypothesis if there's anything, and explore the data analysis. What are the relationships that appear to be there in the data? So just treat it as any other regression problem that we saw earlier. It's just the same thing. So to sum up, we've been talking about classification problems. And then something very important here is how you evaluate the classifier, because as we see, it's very easy to overfit the models. We saw how to use regression for classification, decision trees and random forests, and SVMs. So this is the content of today. If you want to read some more, again, you can go to the book of the course, and there's a nice chapter 9.5 on the relationship between logistic regression and some other classifiers. You have a comparison of different classification methods if you want to read about it. And in this web page, you have different methods for dealing with the problem of imbalanced classes. So how to deal with that when you fit a classifier. More things that are completely optional. There's another technique called boosting. It's essentially what is achieving regularly the best performance in all classification problems. So if you want to read about it, there you go. It's again a very clever idea, I have to say. Section 9.3 of the book talks further about kernels for support vector machines if you want. And 4.4 talks about linear discriminant analysis, which is a very simple classification method based on, again, the linear model. So again, if you want to go further, go to these places. If you want to read more about the contents of today, go to these places. And that's the lecture for today. I don't see any more questions, but anyway, I can stay here a few more minutes. If not, as usual, so the slides are already in Brightspace. I will upload the video recording whenever I have it. I will post it also on Brightspace. Tomorrow you have a lab coming up on classification with Python. There's a set of 10 exercises in there as well. And the grades for A4 are probably going to be uploaded end of this week. So you can stay tuned for that. And I don't think there's much more. Any comments, anything that you have, feel free to just drop me an email and I'll get back to you. So again, I'm going to stay here for questions, and if not, see you next week. Bye.